A planet is a simple thing. You know what a planet is. You've known since childhood. A planet orbits a star. It is roughly spherical. It has a surface or an atmosphere, or both. It is made of rock or gas or some combination. It follows predictable physical laws that we have understood for centuries. Planets are the most familiar large objects in the universe. We live on one. We have visited another. We have sent probes to every planet in our solar system. We have photographed them, measured them, analyzed their atmospheres, mapped their surfaces. Planets are not mysterious. Planets are known. In 1995, humanity detected the first confirmed planet orbiting a star other than the Sun. It was designated 51 Pegasi b. It was a gas giant. It orbited its host star at a distance of approximately 0.05 astronomical units, about 1/8 the distance from Mercury to the Sun. Its orbital period was approximately 4.2 days. This planet should not exist, not in the sense that it violates physics. It does not violate physics. It is there, confirmed, measured, observed. But it is there in a location and configuration that every model of planetary formation available in 1995 said was impossible. Gas giants form in the cold outer regions of protoplanetary disks, far from their host stars, where temperatures are low enough for volatile compounds to condense and provide the material for rapid planet growth. A gas giant at 0.05 astronomical units orbits in a region that is far too hot, far too close to the star, far too lacking in the solid material needed for planetary accretion. 51 Pegasi b forced astronomers to revise everything they thought they knew about how planets form, and it was only the beginning. In the 3 decades since 51 Pegasi b, we have confirmed the existence of more than 5,500 exoplanets. The population includes objects that are stranger than anything we could have invented, worlds where liquid iron rains from the sky, where atmospheric temperatures on the day side exceed 4,000 degrees Celsius, while the night side is below -200. Where the ocean is made of water compressed to a solid state by pressure while being simultaneously above the boiling point, where a year lasts 8 hours, where tidal forces have locked the planet in permanent day on one side and permanent night on the other. Each of these worlds breaks a rule. Each one violates an assumption. Each one requires the existing models to be extended, revised, or abandoned. This video goes through 8 of them. In each case, we start with what we expected, what the physics said was the only reasonable outcome, and then show what the universe actually built. By the end, the definition of what a planet can be will have been broken so many times that it will need to be rebuilt from scratch. There is something in the 6th section of this video that most astronomers who work on exoplanets describe as the most disturbing discovery in the field. Not because of what the planet does, but because of what its existence implies about every assumption we made when we were looking for life elsewhere. Stay with me. The logic breaks early and breaks often. Before we start, what do you think is the most extreme thing a planet could do? Before the universe shows you what it actually built, drop your answer below. Most people underestimate by several orders of magnitude. Let's start with a planet that looks, at first, almost familiar. HD 189733b was discovered in 2005. It orbits a K-type star, slightly smaller and cooler than the Sun, at a distance of approximately 0.03 astronomical units. Its orbital period is approximately 2.2 days. It has a mass of approximately 1.1 Jupiter masses. It is, by exoplanet standards, well studied, one of the most frequently observed exoplanets in the sky, having been analyzed by Hubble, Spitzer, and numerous ground-based telescopes. Initial observations suggested a familiar category, hot Jupiter, a gas giant in a close orbit. Extreme temperatures, yes, but a gas giant. Familiar enough. Then the atmospheric observations came in. HD 189733b orbits so close to its star that it is tidally locked. One side permanently faces the star. The other side is permanently in darkness. The day side receives an enormous flux of stellar radiation and reaches temperatures of approximately 1,200 degrees Celsius at the top of the atmosphere. The night side is approximately 500 degrees Celsius. Cooler, but still hot enough to melt most metals. The temperature difference between the day side and night side drives extraordinarily powerful winds. HD 189733b's. Atmosphere moves at approximately 8,700 kilometers per hour, approximately 7 times the speed of sound on Earth. These winds carry heat from the day side to the night side, distributing it around the planet. This part, while extreme, is physically predictable. Hot Jupiters in close orbits are expected to be tidally locked and wind-driven. What was not predicted is what the winds carry. In 2015, observations by Hubble's Space Telescope Imaging Spectrograph revealed that HD 189733b's atmosphere contains silicate particles, tiny grains of glass and rock, at altitudes where they condense from the hot gas as it rises and cools slightly. These silicate grains form clouds in the upper atmosphere, clouds of glass. On Earth, clouds form when water vapor condenses into liquid droplets or ice crystals. On HD 189733b, at temperatures of 1,000 degrees Celsius, the condensable material is not water. It is silicates, the mineral compounds that make up most of Earth's rocky crust. The clouds on HD 189733b are made of glass particles. They form, they move with the winds, and when conditions are right, when the glass particles grow large enough and reach regions of the atmosphere where the temperature and pressure allow, they precipitate. It rains glass on HD 189733b, sideways. At 8,700 kilometers per hour, not metaphorically, not approximately, the spectrographic signatures of silicate condensate particles in a saturated atmosphere driven by supersonic winds in a direction perpendicular to the vertical, this is what the observations show. Beyond the glass rain, subsequent observations revealed an additional component to HD 189733b's atmosphere that was not predicted by any model: iron. In 2018, a paper by Cabot and colleagues in the monthly notices of the Royal Astronomical Society reported the detection of neutral iron in the atmosphere of HD 189733b. Iron gas. Vaporized iron. Iron atoms suspended in a planetary atmosphere at temperatures sufficient to keep iron in the gas phase. On the hottest part of the day side, temperatures are sufficient to vaporize iron. Iron enters the gas phase and mixes with the atmosphere. The winds carry this iron-rich gas to cooler regions. As the gas cools, the iron condenses, forms droplets of liquid iron, and precipitates. It rains liquid iron on HD 189733b. Not glass, not silicates, iron. The planet has a weather system that produces rainfall of liquid metal at velocities of several kilometers per second, driven by winds moving at 7 times the speed of sound, in an atmosphere where the average temperature exceeds the melting point of most substances you have ever touched. The detection of silicate clouds on HD 189733b was reported in a 2015 paper by Evans and colleagues in the Astrophysical Journal Letters, using Hubble Space Telescope STIS observations of Rayleigh scattering in the planet's transmission spectrum. The characteristic blue color of the planet, confirmed by reflected light observations, is consistent with scattering by submicron silicate particles, similar to the mechanism that makes Earth's sky blue through Rayleigh scattering by nitrogen and oxygen molecules. The iron detection in 2018 by Cabot et al. Used high-resolution spectroscopy from the HARPS-N spectrograph. HD 189733b is extreme. WASP 76b is in a different category. WASP 76b was discovered in 2013. It orbits an F-type star, slightly larger and hotter than the Sun, at a distance of approximately 0.033 astronomical units. Its orbital period is approximately 1.8 days. Its mass is approximately 0.92 Jupiter masses. Like HD 189733b, it is tidally locked. But WASP 76b's host star is hotter, and the proximity is slightly greater, and the result is a dayside temperature that reaches approximately 2,400 degrees Celsius. 2,400 degrees Celsius is above the boiling point of iron. On the dayside of WASP 76b, iron does not just melt, it evaporates. Iron transitions directly from solid or liquid to vapor at dayside temperatures. The iron vapor mixes with the atmosphere and is carried by the global wind circulation toward the terminator, the boundary between the permanent dayside and the permanent night side. At the terminator, the temperature drops. Iron vapor that was stable at 2,400 degrees Celsius is no longer stable at the cooler terminator temperatures. It condenses, forms droplets, falls. In 2020, a paper by Ehrenreich and colleagues in Nature reported the detection of this iron asymmetry using the espresso spectrograph on the Very Large Telescope. The observation used high-resolution transmission spectroscopy to measure the iron absorption signal on the leading edge of the terminator, the edge that the planet's rotation brings into the dayside, and the trailing edge. The result was striking. Iron was detected on the trailing edge of the terminator, the night side edge, where iron vapor carried from the dayside is condensing and precipitating. Iron was not detected on the leading edge, the dayside edge, where conditions are too hot for iron to condense. The planet has an asymmetric atmosphere. The dayside produces iron vapor. The winds carry it to the night side. The night side rains liquid iron. The iron that precipitates on the night side stays there, or evaporates again when it is carried back to the dayside by lower-level return winds. The planet has a global iron cycle. Iron evaporates on the dayside, iron rains on the night side. The cycle is driven by the temperature difference between permanent noon and permanent midnight. On Earth, water evaporates from oceans, rises, forms clouds, and precipitates as rain. The water cycle redistributes water around the planet and drives weather patterns. On WASP 76b, iron evaporates from the dayside atmosphere, rises, is carried to the night side, and precipitates as liquid metal rain. The iron cycle redistributes iron around the planet and drives what passes for weather on a world where the average temperature exceeds the melting point of steel. The Ehrenreich paper described the observation as a direct detection of condensation and precipitation of iron in the atmosphere of a hot Jupiter, confirmation that the extreme conditions on tidally locked gas giants produce weather systems with no analog in solar system experience. No analog. That phrase appears repeatedly in the exoplanet literature. No analog. No terrestrial equivalent. No solar system comparison that adequately captures what is happening. The universe has been building planets for 13 billion years without consulting our models. The Ehrenreich et al. 2020 Nature paper on WASP 76b's iron rain used the espresso spectrograph, the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, mounted on the European Southern Observatory's Very Large Telescope in Chile. Espresso achieves a spectral resolution of approximately 140,000, allowing detection of individual atomic absorption lines in planetary atmospheres. The iron asymmetry was detected at 5 sigma significance, the standard threshold for confident detection in astronomical observations. Now let's move from gas giants to something smaller and stranger. 55 Cancri e was discovered in 2004. It orbits a Sun-like star at a distance of approximately 0.015 astronomical units, closer than any planet in our solar system orbits the Sun. Its orbital period is approximately 18 hours. Its mass is approximately 8.6 Earth masses, placing it in the category of super-Earths, rocky planets significantly more massive than Earth. 18-hour year. The planet completes an entire orbit, its entire year, in less than 1 Earth day. Its surface temperature on the day side reaches approximately 2,400 degrees Celsius, above the melting point of virtually all rock-forming minerals. The surface is not rock in any conventional sense. It is molten. The day side of 55 Cancri e is covered by an ocean of magma, liquid rock, kilometers deep, globally distributed. A planet with an ocean. The ocean is lava. This alone would be extraordinary. But the 2023 observations from the James Webb Space Telescope revealed something that no one had predicted and that required significant theoretical work to explain. 55 Cancri e has an atmosphere, not the kind of atmosphere you would expect from a planet where the surface is molten rock. A thick, volatile-rich atmosphere containing carbon dioxide, carbon monoxide, and other compounds that would normally be expected to have been stripped away by the intense stellar radiation at such close orbital distance. The atmosphere should not be there. At 0.015 astronomical units from a Sun-like star, atmospheric escape, the process by which stellar radiation ionizes and expels atmospheric gas, should have stripped 55 Cancri e's atmosphere billions of years ago. The 2023 JWST observations, published by Hugh and colleagues in Nature, suggested that the atmosphere is being continuously replenished, outgassed from the magma ocean beneath it. The lava ocean is not static. It is volatile-rich molten rock that continuously releases gases from its interior as it circulates, maintaining an atmosphere against the continuous loss driven by stellar radiation. The planet has a dynamic system in which the ocean replenishes the atmosphere and the atmosphere interacts with the ocean. A planetary scale feedback between a magma surface and a rocky atmosphere. A geological cycle operating at temperatures that would vaporize any known biological molecule in microseconds. The JWST thermal emission measurements also revealed something unexpected about 55 Cancri e's heat distribution. The hottest point on the planet is not the point directly facing the star, as would be expected for a tidally locked body with no atmosphere. The hottest point is offset from the substellar point by approximately 41 degrees. The offset indicates that something is transporting heat, redistributing it from the substellar point to a neighboring region. Either an atmosphere with significant heat capacity and circulation, or a subsurface magma flow connecting the substellar region to adjacent areas. A planet with a magma ocean, a rocky atmosphere, and either atmospheric circulation or subsurface lava flows transporting heat around the globe. The geological processes that shaped Earth over 4.5 billion years, volcanism, outgassing, atmospheric evolution, ocean-atmosphere interaction, are happening on 55 Cancri e in a compressed, extreme, unrecognizable form. What Earth did over 4.5 billion years, 55 Cancri e is doing continuously, at temperatures that make Earth's most active volcanoes look like candles. The JWST thermal emission observations of 55 Cancri e were published in a 2024 Nature paper by Hu et al. Using the MIRI instrument's photometric mode. The observations measured the planet's thermal emission at 15 micrometers, a wavelength sensitive to atmospheric carbon dioxide. The detection of significant thermal emission from the night side, combined with the offset hotspot, was interpreted as evidence for a substantial, volatile-rich atmosphere rather than a bare rock surface. The paper represented the first atmospheric detection on a super-Earth using James Webb Space Telescope data. 55 Cancri e is not unique in having a lava ocean surface. Several other super-Earths in close orbits are expected to have similar surface conditions. What makes it scientifically significant is what its atmosphere reveals about the interior. The volatile compounds in 55 Cancri e's atmosphere, carbon dioxide, carbon monoxide, had to come from somewhere. They came from the magma, which means the magma contains these volatiles, which means the planet's interior is carbon-rich. A carbon-rich interior, a magma ocean surface, a carbon-bearing atmosphere. This is a planet whose bulk composition is fundamentally different from Earth. Earth's interior is dominated by silicate rock and iron. 55 Cancri e may have a carbon-dominated interior, a composition that produces different minerals, different geological processes, and a different relationship between the interior and the surface. One proposed composition for carbon-rich super-Earths is a layer of diamond beneath the surface. Carbon, under the extreme pressure of the overlying rock, crystallized into the densest form of carbon. A planet with a diamond interior, a magma ocean surface, and a carbon dioxide atmosphere. This has not been confirmed for 55 Cancri e. It is a theoretical possibility consistent with the available data. But the data is consistent with it, and in exoplanet science, consistent with is the beginning of a conversation that sometimes ends with confirmed. Stop here. 55 Cancri e, a planet with a lava ocean surface, a carbon dioxide atmosphere replenished by the lava, and a possible diamond interior. If this planet orbited at Earth's distance from the Sun instead of 0.015 astronomical units, if it received the same stellar flux as Earth, would it be habitable? Think about what would change and what would not. Drop your answer below. The question is more physically interesting than it first appears. Let's move to the planets that break the temperature scale entirely. HATP 7b was discovered in 2008. It is a hot Jupiter orbiting an F-type star at a distance of approximately 0.038 astronomical units, with an orbital period of approximately 2.2 days. Its dayside temperature reaches approximately 2,600 degrees Celsius. At 2,600 degrees Celsius, the condensable species in HATP 7b's atmosphere are not water, not silicates, not even iron. At this temperature, corundum, aluminum oxide, the mineral that forms rubies and sapphires, condenses from the gas phase. HATP 7b has clouds made of rubies and sapphires. This is not poetic language. Corundum, Al2O3, is the mineral that, when containing trace amounts of chromium, forms the red gemstone we call ruby, and when containing trace amounts of iron and titanium, forms the blue gemstone we call sapphire. The pure mineral without impurities is colorless. HATP 7b's corundum clouds are almost certainly the pure mineral, not the gemstone colors that require specific impurities, but the mineral is the same. The clouds on HATP 7b are made of the same aluminum oxide that forms the precious stones in human jewelry. A 2016 paper by Armstrong and colleagues in Nature Astronomy reported that HATP 7b's cloud distribution is asymmetric and variable. The clouds shift from one side of the terminator to the other on timescales of days to weeks. The wind patterns that drive cloud distribution on this planet are not stable. They are variable. They may even reverse direction periodically. A planet where the winds change direction on timescales of weeks, where corundum clouds form, shift, and dissipate, where the weather forecast, if such a thing existed, would be updated daily not because of pressure systems, but because the global wind circulation itself is changing direction. Now let's go further. Kelt 9b. Kelt 9b was discovered in 2017. It orbits an A-type star, significantly hotter than the Sun, approximately twice as massive, at a distance of approximately 0.034 astronomical units. Its orbital period is approximately 1.48 days. Its dayside temperature reaches approximately 4,600 degrees Celsius. 4,600 degrees Celsius. The surface of the Sun is approximately 5,500 degrees Celsius. Kelt 9b's dayside is hotter than the surfaces of most stars, not hotter than stellar interiors, those reach millions of degrees, but hotter than the visible surface of the majority of stars in the galaxy, which are cool red dwarfs with surface temperatures of 2,000 to 3,500 degrees Celsius. Kelt 9b is a planet hotter than most stars. At 4,600 degrees Celsius, no molecules can survive. Every molecular compound that enters Kelt 9b's dayside atmosphere is thermally dissociated, broken apart into individual atoms by the thermal energy. There are no molecules on the dayside of Kelt 9b, no water molecules, no carbon dioxide, no molecular hydrogen. Every compound is atomized. The atmosphere of Kelt 9b's dayside consists of a plasma of individual atoms, hydrogen, helium, iron, titanium, magnesium, and dozens of other elements in their atomic rather than molecular form. A 2018 paper by Hoymakers and colleagues in Nature detected iron and titanium in Kelt 9b's atmosphere using high-resolution spectroscopy. The detection confirmed that the atmospheric temperature is sufficient to maintain these elements in atomic form, a temperature regime normally associated with stellar atmospheres rather than planetary ones. Kelt 9b is not a planet with a stellar atmosphere. It is a planet in a stellar temperature regime. The distinction matters because the physics of heat redistribution, atmospheric escape, and molecular chemistry are fundamentally different in this temperature range. The planet is losing its atmosphere. At 4,600 degrees Celsius, atmospheric escape is occurring at a significant rate. The uppermost layers of the atmosphere are being heated to temperatures where individual atoms can escape the planet's gravity entirely. Kelt 9b is evaporating, slowly, on timescales of billions of years, but measurably. We can detect the mass loss in real time using ultraviolet observations of the escaping atmosphere. A planet that is visibly, measurably evaporating into its host star. Kelt 9b was discovered by the Kilodegree Extremely Little Telescope, KELT survey, designed specifically to find hot Jupiters around bright stars. The planet's equilibrium temperature of approximately 4,050 Kelvin, accounting for heat redistribution, makes it the hottest known exoplanet as of current catalog. The detection of Fe and Ti in its atmosphere by Hoymakers et al. 2018 used the HARPS N spectrograph at the Telescopio Nazionale Galileo. Subsequent studies have detected more than 20 different atomic species in Kelt 9b's atmosphere, making it the most chemically characterized ultra-hot Jupiter known. Now let's move from heat to pressure, from planets that are too hot to planets that are too dense, from the familiar category of rocky or gaseous to something that has no name in our solar system experience. GJ1214b was discovered in 2009 by the M-Earth survey, orbiting an M-dwarf star at a distance of approximately 0.014 astronomical units, with an orbital period of approximately 1.6 days. Its mass is approximately 6.5 Earth masses. Its radius is approximately 2.7 Earth radii. These two numbers together, mass and radius, define the planet's bulk density. GJ1214b's density is approximately 1.9 grams per cubic centimeter. Earth's density is approximately 5.5 grams per cubic centimeter. A pure water planet would have a density of approximately 1 gram per cubic centimeter. GJ1214b falls between these values. Too dense to be mostly water, too light to be mostly rock. The composition that fits the density is approximately 25% rock and 75% water. A planet that is 3/4 water by mass. Not water in the sense of oceans on a rocky surface, water throughout the interior, a deep water layer covering a rocky core, extending from the surface downward for thousands of kilometers. At the surface, the pressure and temperature produce liquid water oceans, if the temperature is in the right range, which for GJ1214b in its current orbit, it may not be. But in the deep interior, the pressure becomes so extreme that water transitions to unusual states, Ice 7, Ice 10, exotic high-pressure phases of water that are solid despite being at temperatures far above water's normal boiling point. Ice that is hotter than boiling. The phase diagram of water, the relationship between temperature, pressure, and water's physical state, is more complex than the simple solid-liquid-gas picture taught in basic chemistry. At pressures exceeding approximately 2 gigapascals, achievable deep within a water world's interior, water transitions to high-pressure ice phases that remain solid at temperatures of hundreds of degrees Celsius. GJ1214b's deep interior may contain Ice 7, a solid phase of water stable above 2 gigapascals at temperatures of several hundred degrees Celsius. Water that is simultaneously above its boiling point and solidly frozen. Subsequent observations of GJ1214b's atmosphere by the James Webb Space Telescope, published in 2023 by Kempton and colleagues in Nature, revealed a featureless thermal emission spectrum, consistent with an atmosphere dominated by very heavy molecules, possibly water vapor, or with high-altitude clouds that mute the spectroscopic features of the lower atmosphere. GJ1214b is still not fully characterized. Its atmosphere remains partially mysterious. What is clear is that it represents a planetary type, the water world, the Hycean planet, that has no analog in our solar system. A planet that is mostly water. Not water as a surface feature, as it is on Earth, where water covers 71% of the surface, but constitutes only 0.02% of Earth's total mass. Water as a dominant component of the planet's bulk composition. Water all the way down. If life exists on GJ1214b, a question that cannot currently be answered, it would exist in an environment fundamentally different from any environment that produced life on Earth. No rock-water interface on a planetary scale. No plate tectonics driven by a rocky mantle. A global ocean with no continental land masses, overlying an ice mantle, overlying a rocky core that may never be in contact with the ocean above it. Life, if it exists there, would have evolved in an environment that shares with Earth only the presence of liquid water and an energy source. Everything else would be different. The 2023 JWST observations of GJ1214b by Kempton et al. In Nature use the NIR-ISS and NIR-SPEC instruments to obtain transmission spectra across a wider wavelength range than any previous observations of the planet. The featureless spectrum, flat across all measured wavelengths, was interpreted as indicating either a high mean molecular weight atmosphere dominated by water or carbon dioxide, or the presence of high-altitude aerosol particles suppressing spectral features. The observation ruled out a hydrogen-dominated atmosphere at high confidence. Now we come to the discovery that most astronomers in the exoplanet field describe as the most disturbing, not because of what the planets are, but because of where they are. In 1992, Alexander Volshan and Dale Frail announced the discovery of two planets orbiting a pulsar designated PSR 1257+12. A pulsar, not a main sequence star, not a red dwarf, a pulsar, the rapidly rotating neutron star remnant of a supernova explosion, emitting beams of radio waves from its magnetic poles as it rotates. PSR 1257 plus 12 rotates approximately 161 times per second. A supernova, the explosion that produces the neutron star, releases energy sufficient to destroy any planet in the system. The blast wave, the radiation, the gravitational disruption of the system. A supernova is not a survivable event for planetary bodies at close range. And yet, PSR 1257 plus 12 has planets. The planets were detected through pulsar timing. The extraordinary precision of pulsar rotation rates means that the slight gravitational tug of orbiting bodies produces detectable variations in the arrival times of pulsar pulses. Wolszczyn and Frail detected the gravitational signature of two Earth-mass planets orbiting the pulsar at distances of 0.36 and 0.46 astronomical units. A third, smaller body was subsequently detected at 0.19 astronomical units. These planets exist in the radiation environment of a millisecond pulsar. The pulsar emits X-rays, gamma rays, and high-energy charged particles continuously. The radiation flux at the planet's orbital distances is far in excess of anything that any known life form on Earth could survive. There are two hypotheses for the origin of these planets. The first is that they are remnants, that they existed before the supernova and somehow survived the explosion, stripped of their atmospheres and outer layers but retaining their rocky cores. This is difficult to explain physically. The supernova should have been sufficiently violent to disrupt any pre-existing planetary system. The second hypothesis is that they formed after the supernova, from the material ejected by the explosion, gradually coalescing into planetary bodies in the debris disk around the newly formed pulsar. Planets formed from supernova ejecta. Planets made of the material that was once the interior of a massive star, blown apart by the explosion that ended its life, and then reassembled into new worlds around the neutron star remnant. This second hypothesis, planet formation from supernova debris, has implications that extend far beyond PSR 1257 plus 12. It means that planet formation is not an exclusive property of stellar birth. It also occurs at stellar death. Planets can form in the aftermath of the most violent events that stellar evolution produces. The conditions required for planet formation, a central mass, a surrounding disk of material, sufficient time for accretion, can be met in the wreckage of a supernova, as well as in a protoplanetary disk. Planet formation is more robust than anyone suspected. It occurs not just in the favorable conditions of a forming stellar system, but in the extreme, radiation-intense, debris-filled environment of a supernova remnant. If planet formation is possible around a pulsar, in conditions that should, by any reasonable prior expectation, preclude it, then where else might planets be forming that we have not yet looked? And if planets form in the most extreme environments the universe produces, then the question of what environments are too extreme for planet formation becomes significantly harder to answer. The answer, based on current evidence, may be none. The Wolszczyn and Frail 1992 discovery paper in Nature was the first confirmed detection of planets outside the solar system, predating the 51 Pegasi b discovery by 3 years. The pulsar timing method used to detect them achieves extraordinary precision because millisecond pulsars are among the most accurate natural clocks known. Their rotation rates are stable to better than 1 part in 10 to the 13th power over years of observation. A third planet in the PSR 1257 plus 12 system was confirmed by Wolszczyn in 1994. The system remains the only confirmed planetary system around a millisecond pulsar. One more. The last one in this series is the one that breaks the most basic assumption of all. When you look at a planet, it reflects light. That is how we see planets. The moon reflects sunlight. Jupiter reflects sunlight. Venus is the brightest object in the night sky after the moon because it reflects approximately 70% of the sunlight it receives. Planets reflect light. This is a foundational assumption of planetary science. It is built into every model of planetary climate, every calculation of planetary temperature, every estimate of what a planet looks like from a distance. TRES 2b reflects 1% of the light it receives. TRES 2b was discovered in 2006. It is a hot Jupiter orbiting a G-type star at approximately 0.036 astronomical units, with an orbital period of approximately 2.5 days. Its mass is approximately 1.2 Jupiter masses. It is tidally locked. Its geometric albedo, the fraction of incident light it reflects, is approximately 0.0136, less than 1.4%. For comparison, coal, one of the darkest natural substances on Earth, has an albedo of approximately 4%. Fresh asphalt is approximately 4%. The darkest natural substances on Earth reflect 3 to 4 times more light than TRES 2b. TRES 2b is darker than coal, darker than asphalt, darker than anything in the natural world that we normally use as a reference for dark. It reflects less light than a black hole would if observed from outside its event horizon at an angle, which is to say, it is about as dark as a macroscopic object can be while still having a physical surface. How? The mechanism is not fully understood. At TRES 2b's atmospheric temperatures, approximately 1,500 degrees Celsius on the day side, the standard cloud-forming species that would otherwise contribute to reflected light are not present. There are no water clouds, no ice clouds, no reflective aerosols at these temperatures. The atmosphere is clear of the compounds that normally make planetary atmospheres reflective. But a clear atmosphere is not black. A clear atmosphere transmits and absorbs, but gaseous atoms and molecules do not typically absorb across all visible wavelengths with 99% efficiency. The leading explanation involves gaseous sodium and potassium, alkali metals that have broad absorption features in the visible spectrum at these temperatures, combined with titanium oxide and vanadium oxide, which are efficient absorbers of visible radiation at hot Jupiter temperatures. The combination of these absorbers may produce an atmosphere that is nearly perfectly black across the visible wavelength range. TRES 2b may be the darkest planet in the known universe, not because of any exotic physics, because of the specific combination of atomic absorbers in its atmosphere at its specific temperature, a standard hot Jupiter, in a standard hot Jupiter orbit with standard hot Jupiter physics, producing a surface darker than any object in human experience. TRES 2b's albedo measurement was published by Kipping and Spiegel in 2011 in monthly notices of the Royal Astronomical Society, using Kepler photometry to measure the reflected light from the planet during its orbit. The Kepler spacecraft's extraordinary photometric precision, measuring brightness variations to parts per million, enabled the detection of the tiny reflected light signal. The geometric albedo of 0.0136 is lower than any other planetary body measured to date, and significantly lower than the prediction of standard hot Jupiter atmospheric models. A planet is a simple thing, except it is not. It rains iron sideways at 7 times the speed of sound. It rains liquid metal on the night side, while the day side vaporizes the same metal. Its surface is a global ocean of lava that continuously outgasses an atmosphere made of rock. Its atmosphere is hotter than most stellar surfaces. Its interior is water, compressed to a solid state at temperatures above boiling. It formed in the wreckage of a supernova. It reflects less light than a piece of coal. These are not hypothetical planets. They are not thought experiments. They are confirmed, observed, characterized objects in catalogs that are publicly accessible, produced by the same telescopes that you see in press releases about space exploration. They exist. And they violate, between them, almost every assumption that was embedded in planetary science before 1995. The universe has been building planets for 13 billion years. In that time, it has explored a parameter space of conditions, compositions, temperatures, and orbital configurations that our models, built from the 8 planets of our solar system, did not anticipate and cannot fully describe. The most important implication of the exoplanet field is not any specific discovery. It is the systematic demonstration that our sample of one, our solar system, was not representative of what the universe builds. We assumed planets were like what we had.
The universe had been building something far stranger, far more varied, far more extreme than anything we could observe from inside our own system. And we had been cataloging the assumptions rather than the planets. 5,500 confirmed exoplanets, growing every year, each one a data point in a distribution that continues to extend further into the extreme than the previous year's data suggested it would. The distribution has not yet found its edge. One question: of all the planets in this video, iron rain, lava oceans, ruby clouds, a planet hotter than stars, water compressed to hot ice, pulsar planets, a world darker than coal, which one do you find most disturbing? Not most extreme, most disturbing. There is a difference. Drop your answer and tell me why. I want to know which one changes how you think about what a planet is.
Next video, dark energy, the force constituting 68% of everything that exists, responsible for the accelerating expansion of the universe, with no agreed physical explanation and no representation in any confirmed theory of physics. The Nobel Prize was awarded for discovering it. No one has explained what it is. See you there.